You know that feeling when you're staring at a spreadsheet, just this wall of numbers, and your eyes just glaze over? It's completely overwhelming, right? Well, what if I told you there's a really simple way to make all that data actually tell a story? Today, we're going to do just that. We're going to turn those confusing columns of numbers into clear, insightful pictures. So here's our game plan for today. We're going to kick things off with the big why. Why do we even bother graphing data in the first place? Then we'll meet our star player for this explainer, the histogram. After that, we'll learn how to actually read it, decode its story. We'll explore the common shapes data tends to make, and we'll wrap up with a pretty cool pro-level technique for checking if your data fits that perfect bell curve. Sound good? Let's dive. Okay, so first things first, why are graphs such a big deal? I mean, seriously. Imagine I just hand you a list of, say, 50 different commute times, just a raw column of numbers. Could you spot any patterns just by looking at it? No way. It's just noise. We need a way to see the forest for the trees. And this quote right here just nails it. Look, you could organize all that data into a table, right? Group the times into different buckets. And that's a decent first step. But a histogram, oh man, it does something that feels almost like magic. It turns that boring table into a picture. And our brains are just wired to understand pictures. We can spot patterns in a split second that a table of numbers would hide from us completely. All right, so let's put this powerful tool under the microscope. What exactly is a histogram anyway? Honestly, it sounds way more complicated than it is. Just think of it like a bar chart, but the bars are all squished together, no gaps. So along the bottom, that's your horizontal axis, you've got your data sorted into these little buckets or bins. Things like commute times from, say, 0 to 15 minutes, then 15 to 30, and so on. And the vertical axis, that's just a count. The height of each bar tells you how many data points fall into that specific bucket. That's really it. Taller bar means more stuff in that category. Okay, let's make this real. Here's an actual histogram showing commute times. Just look at it. See that tallest bar right in the middle? Instantly, without doing a single bit of math, you know that the most common commute time is somewhere in that 22 to 37-minute range. That right there is the power of a visual. You get instant insight. And that's really the magic of it. In just one glance, you get the whole story. You can see the overall shape of the data, you can get a feel for where the center is, you can see how spread out everything is, and you can even spot the oddballs, what we call outliers, those values that are way off from everything else. Now, really quick, there's a variation on this called a relative frequency histogram. Okay, don't let that fancy name scare you. It is the exact same graph. The only tiny little change is on that vertical axis. Instead of showing the raw count, like 18 people, it shows the percentage, like 35%. So let's put them side by side to see what I mean. On the left, you've got the standard histogram. That tallest bar shows about 18 people. Now look at the right. That's the relative frequency version. The tallest bar there represents about 35% of the total. But, and this is the important part, look at the shape. It's absolutely identical. The story the graph is telling you doesn't change one bit, only the labels on the side do. Okay, so we've got a handle on what a histogram is. Now comes the really fun part, learning how to actually interpret what it's trying to tell us. And believe it or not, there's a simple, systematic way to do this. If you want to analyze a histogram like a pro, all you have to remember is a simple little acronym, CVDOT. C is for center, where's the middle of the data? V is for variation, how spread out is everything? D is for distribution, what's the overall shape? O is for outliers, are there any weird values that don't fit? And T is for time. Now this one's optional, but it's about whether the data has changed over time. So for the next few minutes, let's really zoom in on that D for distribution, the shape. Because here's the cool thing, data doesn't just make random blobs. It often falls into a few common, very recognizable patterns, and each one of those shapes tells a totally different story. And here are the big ones you'll run into most of the time. You've got the famous bell-shaped curve, also called a normal distribution. You've got the uniform distribution, which is kind of flat like a rectangle. And then you have what are called skewed distributions, where you can see this tail stretching out to one side or the other. Let's start with the absolute rock star of distributions, the normal distribution or the bell curve. I mean, you've probably seen this before. It's perfectly symmetrical, like a mirror image. Most of the values are all clustered right there in the middle, and then they get less and less common as you move away from the center. And what's really amazing is how many things in the real world, from people's heights to the arm circumferences we see here, naturally fall into this beautiful, balanced shape. But of course, not everything is perfectly symmetrical, right? So, what happens when the data is lopsided? Well, that's where this idea of skewness comes in. A skewed distribution is just one that isn't symmetric and has a long tail that stretches out more to one side than the other. So here's a great example of what we call skewed to the right. See how most of the data is piled up on the left side, but then you've got this long tail of values stretching way out to the right. A classic example of this is income. Most people earn a certain amount, but then you have a few very, very high earners that create that long tail off to the right. And you can probably guess what's next. This is the opposite. It's skewed to the left. This time the tail points to the left. That means most of the data is piled up on the higher end, on the right, but you've got a few unusually low values pulling that tail out. A good way to think about this is scores in a really easy test. Most students do great, so they're on the right, but a couple of students might have had a bad day, and they create that tail on the left. So a histogram can look kind of bell-shaped, but how can we be absolutely sure it's a real, true, normal distribution? Looks can be deceiving, right? Well, for that, statisticians have this really clever tool designed for this one specific job. It's called a normal quantile plot. Okay, now the math that goes into creating one of these plots is pretty intense, but actually reading one, it is incredibly simple. You just have to look for one thing, a straight line. Seriously, that's it. If the dots on the plot form a pretty straight line, then your data is normal. If they curve or they scatter all over the place, it's not normal. It's just a simple visual check. Take a look at this one. This is a perfect example of what you want to see for a normal distribution. See how those black dots are just hugging that straight green line? Yeah, they aren't perfectly on it, they never will be, but they clearly follow that straight line pattern. This is our signal that the data is normal. Now compare that last one to this. The points here, they clearly do not follow a straight line. You've got this big cluster on the left, and then they just kind of scatter away from the line. This is a huge, flashing sign telling us this data is not from a normal distribution. And finally, here's another way that data can fail the test. The points aren't just scattered randomly this time. Instead, they form a very clear systematic curve. And since a curve is definitely not a straight line, our conclusion is the same. This data is not normal. And there you have it. We started with a confusing jumble of numbers, and now we know how to make it tell a clear, compelling story using a histogram. You can spot the shape of the data, you can find its center, and you can even run a pro-level test to see if it fits that classic bell curve. So the next time you see a chart like this, maybe in a news article or a report for work, you won't just see a bunch of bars. You'll see the story. You'll see what the data is really trying to tell you. The only question left is, what story are you going to uncover first?